intervention, more like a social intervention in the public policy literature, okay? And our example of social intervention would be in terms of a Mexican publicly available data set. The data set is so huge, I just took a 60% of the random sampling of that data, and then I'm going to demonstrate that. So recall the way we want to think about it, it's like the any network analysis when you do. Mansky has a famous book actually. So the book is title is Identification Problem in Social Sciences, okay? And the book talks about that, like there would be an estimation bias. Then Ulrich went on something like consistency of individual over time, because I don't observe them repeated cross section. And then there could be, as I mentioned again and again, the selection on the observables, right? So what is the confounding factor which determines these guys? And the objective, the way we want to think of that we want to basically find out the average causal effect of the intervening variable or of the public policy change variable, which in general is dependent in nature, right? So, sorry, is binary in nature. And your dependent variable could be continuous. They could be even a binary. So it could be something like, job participation in the formal labor market, in the informal labor market, which would be binary in nature. So given then, suppose you have now participated in the formal labor market or in the labor market, how many hours you have worked. That's a continuous variable. But everything we will start thinking of in terms of policy intervention, or if there is a policy change that has occurred. And Mexican case is kind of interesting, and I'll go when we come to the Mexican case. So note what we started with, that DID is actually preferred estimation strategy when we have a natural quasi-experimental design. Okay, clear? So then in those cases, we prefer to do DID because data was not designed ad hoc as a controlled experiment. And there are some ways people talked about it, like Angrist and Piske, or Ashenfelter and Card. And then what we do in case of DID, if you recall, we take two variables or any outcome variable before and after, and then we call it the treatment group and the control group, pre and post, and we try to evaluate the impact of the social intervention, right? That's what we did in case of simple DID. Then Ravelian also, or Ulrich even, talks about that DID could be estimated as a difference on the means between groups rather than individual through non-panel repeated cross-section. And that's what the emphasis with going to be, that I have the data set of individual, for example, national sample survey, where the same individuals are not being surveyed every year, right? Whereas in case of IHDS, you would see that same individuals are being surveyed every year. Yeah. So there is a tracking problem, and hence identification or misidentification of the group between periods could lead what we am going to call is a biased result. And of course, the standard error, recall we talk about standard error in terms of yesterday's last slide, the double robust estimation, that also would turn out to be serially correlated. A solution could be cluster standard error and to work them as fixed effect. I'm going to come to those issues a little bit later. It's a little different, but we'll deal with it. So recall the DID estimators we started talking about, that I have two groups, program is being implemented, somebody got exposed to the program and somebody did not. But all I want to think of that I am interested in the coefficient of the interaction term, which in this case is beta 3, and I'm going to evaluate them between the two groups, which one group got exposed to the program and one group did not get the exposure to the program, right? That's what we were. Now, If I think of the DID estimator with the repeated cross section, then I want to think of pool cross section is a better way to do it. So all I do, I basically paste the data one after the other. So NSS round 65, then 70, then 72, 74, I do that. And then I want to think of, there are three different ways I can think of the estimation strategy. One, estimation of the average effect on the mean of the group of interest. But in this case, recall, I'm going to use a repeated cross-sectional methods or RCS, okay? The second one I can think of that the average treatment only on the treated, clear? So first is my ATE, then my ATT, because it is average treatment on the treated based on the propensity score matching method, okay? So some people got treated, some people did not, but I'm going to evaluate those guys only who got treated, and hence I'm calling it as average treatment effect on the treated. And the latest one, we would visualize it. It is like my and one of my students. We never submit the paper. I don't know why. I mean, maybe we'll submit at one point of time because still nobody has done it. And to build a synthetic panel to estimate the average effect. I mean, there are at least 10 of my those papers are lying like that over the time period which I lost interest or I never do anything with that. Clear? So that's the issue here. So I'm going to do something like more like a construction of synthetic panel to estimate the average effect. Okay. DID estimator, fast estimation strategy. Recall your fast estimation strategy. The fast estimation strategy, I want to think of estimation of the average effect on the mean of the group of interest using an RCS method. Okay. So the way I want to think about it, the DID is nothing but the first equation. So YST what? My dependent variable for cross section I, which is individual in my case, where in either the treatment or in the control group. And when am I observing this? At time period T. What is alpha? Alpha is the constant. Time it is a dummy for individual in period, individual I in period T after the social intervention is being used. Okay. So I implemented the program and I want to think of these are the individuals. They are in that group where they are getting the benefit of the program. And then treatment ST is a dummy which identifies the treatment group from the control. So it differentiate the guys who are getting the treatment from the guys who did not get the treatment. Clear? And then I have a matrix I can think of Q control variable, and then time times the treatment, as I said again and again, represents my DID estimator, right? So beta 3 is nothing but my impact of social or our impact of social intervention as what? As the difference between the two parts. This is the impact on the control. This is the impact on the exposed group, and I take another difference, and hence I call it before and after its introduction. Absolutely clear, right? Fine. So
it would be a case that in the initial period, the individual will differ from the next
that
period.
doesn't matter, right? All I want to do, I want to paste the data or append the data one after the other. You got the program, I didn't get it. You may not be there in the sample next period, but there could be someone like you who were there in the next period who got the program. Clear? Fine. So that's the way I want to think about it. Okay. DID estimators, the second way to think about it, DID identification consists in the estimation of average treatment effect of the treated, right? So note, I'm now differing from the first one and I'm going to concentrate on ATT. So because it is the average treatment effect on the treated or of the treated rather, okay? In the non-panel cross-sectional contract, so I do not have any panel. I have only cross-section of individual and I want to think about it. The ATT then would be defined as what? ATT are the people who got exposed to the program in period T or period 2 minus the same group of people who did not get the exposure, right? Provided the program takes place. So the way I define it is nothing but yi2 is the outcome variable in period 2 after the exposure. yi1 is nothing but is the people who did not get the exposure, and then this is nothing but conditional on when they got the exposure. So I'm taking ATT as the expected value of the difference in outcome before the treatment and after the treatment, under the condition that those guys have already got the treatment. You see, that is why I'm calling it average treatment effect of the treated. Clear? So for periods 1 and 2 are computed according to the nature of the dependent variable. So it could be a binary, it could be a continuous. The reason behind this estimation, people could or could not be exposed to the treatment. So as I said to you that I don't observe both set of people. The set of people for whom the variable takes the value of 1, and for the set of people or other set of people for whom the variable takes the value of 0. Clear? Fine. So one way that people can think about it, that suppose I have this cross section of huge units of the data set, and I want to think of that whether the in-house R&D fosters my productivity or not. I do not know whether I would be able to see them over the time period or not, the same unit, but at least I can see them in one period and then next period and next period. But I know that the group of IDs, the group of firms would differ across the time period, because I do not have any identification or any identifier to identify those firms in my repeated cross section. Okay. One of the way you can think about it, that how do I do it then? One way to think about it, I want to build up a synthetic panel here. So how do I measure the synthetic panel? One of the way I can think about it, look, the synthetic panel could be something like based on the age of the firm. So I make a age of the firm like my panel identifier. For each group of 5 years, I basically put all those units in the for whom the age is 0 to 5, 5 to 10, and I proceed in that way. So here note, my identifier is nothing but age, right? Panel is a very funny thing actually. You know, the way I can think of a panel, that suppose you are working with national sample survey, right? Or for that matter, what was the other thing? The NFHS, right? The Family Health Survey data set. But there also I can form a panel. How do I form a panel? Because I know the kids belonging to a family. So instead of my normal I and T, I could have I and J there. So I are the kids and J is nothing but the household. And that's my panel. So I want to think about intra-household differences that I am going to call, or I am going to differentiate the intra-household differences by simply introducing the dummies at the household level. Clear? So I basically think of that kids differ from each other simply because their household constitutions or composition is different. Hence, I am going to construct the panel based on I and J, where the J is the household and I are individuals. Same way, I can think of another dimension of the panel. I now can think of people in village J speaking in different languages. So you think of it, I then can control for language effect. I then can control for village effect. I, of course, have the individual staying in village J, speaking in language K. So that's a three-dimensional. So in general, we can think of like we work with the 2D model, but there could be panel where I can easily make the panel as a 3D model, and there I need to control for both that the household effect or the village effect and then the language effect there, because I want to think of that if they speak the same dialect, the communication would be better, and hence their performance in terms of any activity could be nothing but because they share the same dialect.
So I am sorry, I'm not clear about repeated cross-sectional sample. So you mentioned that NFHS, NSS data is repeated
Yeah.
cross-sectional.
Yeah, because there is no way you can get an identifier of the individual in the NSS data across the different rounds of NSS. So think of NSS started with consumer expenditure survey, where the different individuals are being surveyed across the time period.
Is it individual data or a household
It is
data?
individual data. NSS also has the individual data, right? People are being asked, along with different characteristics, like they are being asked something like, what should I say? They are being asked
Education.
about their education, their consumption pattern. Then there was a debate with recall of the consumption pattern, whether 7 days versus 30 days. Then there was this Tendulkar committee. Then there are different things. And, NSS is the primary source of calculating different kind of poverty estimates in context of India. Then also you have some characteristics of the household, like how many members are there, how many members are above age 6, below 60, and things like that. Then you have also the educational status of the household head. Then you have the caste and the gender of the household head. Okay, so some data, but that does not mean that the individual who is being surveyed always going to be the household head. That's the characteristics of NSS. Now, suppose you have the NSS done in 2012, and then after 5 years, there was another NSS 2017, right? There is no way you can match the individuals which is being surveyed in 2012 would be the same one in 2017. Okay, so there is one way. There is only, I think there is a data set in India now which they call it time use survey, and which is kind of the panel, because a lot of people started working in terms of the value of the household work. Okay, so how do you put a value when there is no market wage available? So that's like the time use survey data is available from NSS actually. Okay, so that's what my point is.
So in repeated cross-section data, same household is surveyed, but
No,
not the
no,
same
no, no,
individual.
no, 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 no. It is not the same household. I don't have the identifier which I can match across the round, and that's why it is repeated cross section.
So in 2012, there
Whoever it
was
is,
one.
I all I know, HHID, II, or individual ID, and that's it. That HHID may be, by God's gift, could match with the next round, but it doesn't mean that they belong to the same household.
Okay. Same questionnaire, but
Different
individual.
household, different individuals. That's the
So now we are in a setting where we have repeated cross sample and we don't
repeated.
have a
Yes, I
don't
don't
have
have
a
any
panel.
identifier to make sure that they are the same.
Thank you.
That's why I'm calling it is repeated. But then my point was I can actually make it a panel in a very different way of constructing panel. I can have a pure cross section, but from pure cross section, I can get a panel by just assuming individuals staying in village, a particular village, because I know the village identifier. Okay, so all those individuals in the village are, instead of my I, which is the individual, and T, now T is being replaced by J, where J is nothing but the village. Clear?
J is the village.
Yes. So with the hope that the I, the individual belonging to J, form my panel, or individuals belonging to household J staying in village K form my panel. That's again one more dimension I am adding here. Just individuals and village, from that domain, I am moving to individual, household, and village. So there are three domains that I am introducing. So then I can have a household effect, I can have a village effect. In the first case, only I can have a village effect. Clear? That's how I want to think about it. Huh?
That's the setting now.
That's the setting I want to think about. Okay. Now, first setting I'm going to talk about, I just have to, have a pure cross-sectional data. Clear? Okay. So propensity score, how do I do it? That I want to think of that I do not observe both of them, or I cannot. So I want to go in the domain of propensity score. So what is the propensity score? I'm going to estimate something based on the characteristics of the covariates. Okay, and I'm going to claim that based on the characteristics of the covariate, I'm going to build up some scores, whatever the scores is. And then people with the similar score can be then divided into two groups. Okay, and one group with the similar score may got the treatment, and the other group did not get the treatment. So my counterfactuals here of creating a group with the similar score but did not receive the treatment. Hence, I can observe the people with the similar score got the treatment, but not at the same time people with the similar score who did not receive the treatment. But actually, I can make the differentiation between the two only based on this calculated propensity score. Okay, fine. That's the basic way of thinking of what does the matching or the propensity score implies. Okay, it's basically a different way of matching methods. Sure. Yeah. It can be an exact match. It may not be an exact match. And I'm going to exact match finding is very difficult. And then we are going to think of that what kind of matching we do. How do I ensure that the matching is good, or the way I calculated the matching procedure is good, which is nothing but known as the balancing test. I can define a range that, like if the score that I have calculated based on the covariates, if it is lies between like plus minus 0.2, then I would say it is a good match, which is nothing but gives us the domain of radius matching. Right? Clear? I can then do it something like a nearest neighborhood match, okay, where I can do it by 1 to 1 or 1 to 5 or 1 to 10, whatever. I can vary those guys. Okay, I'll come to that. Clear? So what I want to do with the propensity score, right? So note, matching is an approach to condition on X. X is what? The set of the controls on between a treatment and a control group. So for each observation in the treatment group, what I want to find out is something like statistical twins. And the twins is the clone. And clone must be there in my control group. So the clone shares the same characteristics. However, clone did not get the treatment, right? And somebody else got the treatment. Your point, you see that exactly same or at least very similar X values, the values of the control. The Y values of this matching observation are then used to compute what? The counterfactual outcome. Recall what I said, that got the treatment, did not get the treatment. Clear? And without the treatment for the observation at hand, because I shared the similar characteristics, but because I was fortunate, I got the treatment. How do I think that I was fortunate? Because my village has the program and your village did not have the program. So I got the access to the program, but you did not get the access to the program. Okay. And then an estimate of the average treatment effect can be obtained as the mean differences between those observed values and the imputed counterfactuals, right? Because remember, these are imputed one because I don't actually observe them, right? Clear? Over the all observations. That's fine. Okay. Formal definition. So in terms of the formal definition, what I am doing, I'm basically thinking of that I have the average treatment effect, where the average treatment effect of the ATT, I'm going to sum the difference between what? YI and their deviation from YI0. because that I have estimated, right? And then I'm going to take the sum for period t is equal to 1. I'm going to take the average of the sum because I am calling it average treatment effect on the treated or of the treated. Look, the second one. How does the second one then differ? In case of second one, I'm just going to take this is t is equal to 1. Here, the difference it is t is equal to 0. And then I am replacing this t is equal to 1 by t is equal to 0. Then what am I doing? I basically observe those guys in, I observe those guys in period 1. I take the deviation of these guys from any other person, from any other guy, right? So that's my yi, where I define my yi1 is some weight, think of some weight as wj. So it's kind of like a linear combinations with the weights wij times yj, and I basically calculate them for period t is equal to 1. Whereas for these guys, I do it for period t is equal to 0. Okay. So this is average treatment effect of the controls. And what is my ATE then? ATE is nothing but the weighted average of ATT and ATC. How does the weight differs? I have n number of people, right? I divide the n number of people into two parts. The guys who got the treatment, T1, and the guys who did not get the treatment, T0. So proportion of the guy who did not get the treatment, which is nothing but n, T0 divided by n. Proportion of the guy who got the treatment is n, T is equal to 1 divided by n. For the guy who got the treatment, I take the ATT hat. For the guy who did not get the treatment, I take the ATC hat. And then I take the weighted average of the two, and then I call it, it is nothing but the average treatment effect. No differentiation between treated or the C, which is the control. Clear? Fine? Yes.
So why are we taking average treatment of, why are we adding the?
Because the concepts are, okay. So somebody got the treatment. What would be the impact on them only? Which is ATT. First, listen carefully. Second could be, you did not get the treatment, but what would have happened to you if you have got the treatment, which is your ATC. Okay? And then your average treatment effect then would be the weighted average of ATT and ATC. What would be the weight? A section of the farmer who got the treatment. Clear? And a section of the farmer who did not get the treatment. And the sum of the two, the section of two different types of farmer who got the treatment, who did not get the treatment, constitute your total sample. That's the sample of farmers. So you have 400 farmers in your sample, 150 got the treatment, 250 did not get the treatment. I calculated the impact on the 150. I then calculate what would have happened to those guys who did not get the treatment if they were being exposed to the treatment, right? And then that's my ATC. What would have happened? Hypothetical scenario. Clear? And then my ATE is nothing but actuals and the hypothetical. But I just cannot take a plain simple sum of the two. All I want to do, people got exposed to the treatment and people did not get exposed to the treatment. Proportion of these two groups are my weights in my ATE hat. Clear? Fine. People who are using sophisticated spray are able to export to Europe in your model, right? People who are not able to use sophisticated spray can export but not to import. Now think of this, the people who are not able to use sophisticated spray, if they were given a sophisticated spray, what would have been the impact on them in terms of export to Europe? That's my ATC. First one is very clear, my ATT. Now, I have this group, two groups of people, got it, did not get it, but what would have happened to them? And then the weight is nothing but your ATE. Clear?
Yes, sir.
That's how it is. Yes.
So this predicted value of y is 0,
Yeah.
that is the before treatment average.
Yes. Yes.
So why is it already predicted? We know that.
Yes. Because I know the characteristics.
Right.
Based on that, I calculate the value. What would happen to Hariam with this kind of characteristics in terms of his labor market participation predicted value?
And then we are just comparing after the treatment.
Absolutely. And then in the next case, I'm just doing the process reverse way.
So I knew the values after the
I
treatment.
just basically, yes, right, right.
Then comparing with the previous.
Yes, because that is, if you have got it, then what would you do? But you actually, in reality, you did not got exposed to that. Okay?
J in that case is a time?
J is conditional on J provided T. So that's like a group.
Like we were discussing earlier.
Yes. So that's like the group.
Is this a panel?
No, 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 no. It is like, okay, what should I say? Treatment was applicable to a group of people. So J conditional on time period 0. Then J conditional on time period 1. Now,
For which T is
where, yes, T is equal to 0 and T is equal to 1. But I may belong to that group and I do not belong to that group. That's my I. That's my individual. Program gets food for work program got implemented in a village, right? For a certain group of people who lies between the BPL or something like that, income threshold. You get 183 days of work or something like that, right? So that's the way you want to think about it, before and after. But that would be applicable only for a group qualified with certain characteristics. But it does not mean that even if you qualify, you would participate. Suppose you did not participate, but what could have happened to you if you would have participated? That's my next one. First one is nothing but I know what would have happened to you because you have participated. Now the total effect is nothing but weighted average of these two groups. How do I determine the weight? Simple, proportion of the people who have participated, proportion of the people who did not. Yes, please.
Sir, theoretically it sounds okay, but when I'm trying to visualize from the data perspective,
Yeah,
so if you say that yes, assuming that how the control group might have
behaved.
so from where do you get the data?
Yeah, I'll show you. Exactly. That's what the beauty of the propensity score lies. That is where the beauty of the propensity score lies, okay? And I'll show you. Good question. I'll show you that immediately. Fine. So note, somebody asked me before, exact matching. What is the exact matching? How do I decide Wij? Recall my Wij, right? That's my Wij. So I want to think of Wij should be equal to 1 over Ki. When Xi is exactly same as Xj and 0 otherwise. So your age, your education, your this, your that is exactly same, right? But it's very hard to get on multi-dimensional basis two individual sharing the same characteristics, age, education, family background, income, whatever way you want to think about it, right? So on a multi-dimension basis, it is very difficult to match all the characteristics of individual I with individual J. Okay? Then that's what I want to think of. If X contains several variables, there is a large probability that no exact matching I would be able to find. And what would happen? Always my Wij would turn out to be equal to 0 because there is no exact matching, right? So what I do, one of the way to think about it, that I want to move away from this exact matching and introduce two different concepts of matching, which is the covariant matching. And the covariant matching depends on distance based measure, right? What is the distance based measure? So the way I want to think about it, two individuals in terms of their covariant values. So I have individual A and individual B. Individual A is 25 years old, graduate. Individual B is 27 years old, but high school. Clear? So this is their different characteristics, and I want to take them and I want to employ something like a distance based measure, the similarity of the two individuals in terms of their covariate. So first I want to calculate the distance based on those characteristics. I then want to specify that what would be the permissible distance that I would allow, and this permissible distance that I would allow would become something like two different type of estimator. One would give you a nearest neighborhood estimator, and one would give you a broad like Mahalanobis distance based estimator. Okay, so note what I want to then think of in this case, your point I'm coming, that non-treated and treated groups become only randomly different based on the covariates. So based on the covariates, I'm now creating already the counterfactual, right? Because people now you can think of, they are sharing the same kind of distance based covariate characteristics. Even if I do not observe them, I now know their characteristics. I know people who got exposed to the program, their characteristics. I know their benefit, and hence I can replicate that with those guys who did not get the benefit. Okay, so given this, what I then want to think of, that outcomes of the matched non-treated and the treated groups which keep the originally observed value are comparable under the matched covariate condition. You see that? They are comparable under the matched covariate condition. You did not get that treatment, but you shared the same characteristics like him and he got the treatment. Okay, clear?
Okay, one concern is once you're identifying this covariate.
Yeah.
Now, this covariate could be like, for instance, you're talking about age or maybe education. That might also be the covariate for the variable of interest.
Possible. That's the,
In that case,
yeah.
so whether we should do matching based on it or whether we should control for it once.
No, but in general, what happens that you need to, that's why you need to make sure that what is the objective of this matching exercise. So in general, if you observe that the matching exercise would depend on participation in the labor market or income gain from a subsidy program or something of those, or in firm performance based on some R&D based incentive, right? Yeah. So that's, and then you know that there are these characteristics which could affect the firm performance, right? But I know that R&D based incentive, some guys got it and some guys did not get it. So I'm going to match based on the characteristics which affects the firm performance, right? So I'm going to match them based on age and whatever you want to think about it. So that's how we solve this problem, that what should I use in terms of the covariates, right? So covariate matching, match individual based on the similarity of their covariates. In practice, it is impractical to match directly on the covariates because of the curse of dimensionality. I called it as a multidimensional problem, if you recall. And then what I want to do, covariate matching, I'm going to use the distance based measure. And one of the distance based measure which is extremely popular in the literature is Mahalanobis distance based measure. Okay, and here I want to think of, calculate the similarity of two individuals in terms of their covariate value, and then based on the covariate value I calculate the distance. Okay, non-treated and the treated groups become randomly different, as I said before. So how does exactly Mahalanobis work, or two matching method work? Note, I am still not in the domain of propensity score matching. I'm just in the domain of matching, and then I'm going to bring the propensity score. Okay, so I'm matching methods. There are two different approaches I can think about it. One is the nearest neighborhood. What is the nearest neighborhood? We simply match each individual in the treatment group as the treated unit, of course, with an individual in the control group. Based on what? Based on closest distance between their estimated Mohl-Novice distance matrix. So at any case, you are going to calculate Mohl-Novice distance matrix. Then given the Mohl-Novice distance matrix, you are going to match them as what? Closest distance. So if you do 1, so that means the closest distance must be, the periphery must be 1. If I do 5, then that means the periphery must be 5. So that's how I want to think of. And the way I want to think of matching with replacement keeps bias low at the cost of larger variance. So there would be issue like I draw someone, shall I replace that guy? Okay, and there is a bias and variance trade-off here. So mean variance kind of trade-off. Okay, so the way I want to think of, if I do it with replacement, that would keep the bias low but increase the variance, okay, of the estimator. Bias is lower when employing matching as opposed to without replacement. Why? Because note in this case, suited control units can be used more than once. I pick you, but then I have replaced you. So you still stay in the original sample. Okay, and with replacement as matches for treated units, right? So, the probability of the bias is going to go down if I can do something like with replacement. Okay, such a strategy would actually ensure you to a better balance between the treatment and the control. As why? As I do not want someone being picked and I do not want to replace them, because that would give you a worse control, because those guys should have been there in the control. As I have picked them on the first place, I did not replace them, and hence the probability of the next stage matching would be worse. However, if I could have replaced them, right, then the probability of a better matching arises. Okay, and that's the entire logic between with and without replacement. What is the covariate matching in terms of Mohl-Novice distance? So the way we want to think about it, I have to say a set of individuals I and j with their characteristics, right? So xi is their characteristics for individual I, and xj is the characteristics for the individual j. What you want to do, you want to create the Mohl-Novice distance measure. How? So you take the difference, then you take the covariance matrix of the x, and you again multiply that with the difference. If you recall, like the norm of the two vectors, right? It's something like a concept where it is the norm of the two vectors being applicable. So in some way, it is nothing but the norm of the two vector, where vector A represents the characteristics of individual I, vector B represents the characteristics of individual B, and think of that is nothing but the norm of the vector. Clear? Fine. So that's how we calculate it. So in general, the practice is we use a kernel with a automatic data bandwidth selection. Okay. So that's how, because remember we talked about age at some point of time in the class or in the lecture. Recall, I vary that age, minus age, plus age, and that's like my bandwidth, and it is going to kick in over here again. Now, next one is I want to think of caliper or the radius matching. So here, similar to the nearest available neighborhood matching, but with an additional restriction. So what is the additional restriction I want to impose over here? Both the treated and the controls are randomly selected, right? Are randomly sorted. And then first, what I do, I take the treated unit to find out the closest control match in terms of a propensity score. Okay. but only if the control's propensity score reaches within or stays within a certain radius or not, right? So I can have the propensity score of 0.5. I decide I am going to allow a radius of 0.01. So then I can think of this is zero point 0.5, that my center or the score. I am allowing 0.01 of a radius. So 0.01 of that 0.05, whoever comes, I'm going to pick them up. Clear? As my controls. So the way I want to think of that, I first sort them, the treated and the control, then select the treated unit and then match it with their control, but based on a radius, not like a 1-to-1 distance or distance of 5, based on a radius. And the radius matching is also as a name known as the caliper matching. So in this method, it is possible that a treated unit cannot be matched to a control unit. So there could be something like within that circle, nobody lies, right? So then it would turn out to be no match situation. And then that observation, when I calculate the matching estimator, would be completely discarded. Okay, so because I need to find out this precise based on the circle of whatever you have decided. The,
What you just said that is that the one which we call as case control method?
yeah, you can think of it like the nearest neighborhood. So the radius method is similar to the caliper, right? But removes the restriction. Instead of matching a treated unit with its closest control within a caliper, all the units that fall within that radius are going to be selected, right? I'm not just going to do that the closest within a caliper. Whoever comes under that radius, I'm going to pick them. But if you don't come under the radius, you would be discarded. I'm not going to take you into account.
There are many comes.
I'll take the many. If many comes, I don't have any problem, right? Problem would be if I don't get any one of them.
So then we will use all of them as a match.
Whoever comes in that radius, right? Whoever comes in that radius, I'll take them. But if you don't come, I'm not going to take you. Clear? Kernel. So what I then want to think of, I want to go a little more in terms of the kernel. Again, same kind of things, same kind of kernel, data dependent automatic bandwidth. But here, what I am going to do, I'm going to do the matching so that more close you are, you would get more weight compared to you are far away from someone. So if you are closer to your treated group, you will get higher weight compared to the fact that if you are far away from your treated group, right? So basically it is kind of weighing scheme where closer you are, you get more, farther you are, you get less. Very scientific way to think about it. Xt depends on xt minus 1 until xt minus k. Far you are from time period t, your weight should go down. And exactly that is the way this kernel matching works. Okay?
How does it differ from nearest neighbor? That is also whoever comes very closely we will take.
But in a probabilistic sense. In a probabilistic sense, I'm going to, yes, in a probability sense. Okay? And the last one is basically entropy balancing. And here what I do, covariate and propensity score, two most popular matching techniques. But there exists another one that's now becoming very popular. How does it work? It's a data pre-processing procedure. So what does that mean? I'm going to basically, I'm not going to look at the balancing of the covariates after I do the matching exercise. Rather, I do the covariate balancing first and then I start matching them. What do I mean by the covariate balance? Note, I can do the covariate balance based on mean. That's my covariate balance based on the first order moment condition. I can now do the covariate balance not only based on mean but as well as your variance. So that's nothing but the balancing based on my second order moment condition. But I'm going to be very picky here. I'm going to pick the people fast based on you satisfy what kind of moment condition I want to impose on you based on your characteristics. Once I do that, then I'm going to get those guys who are closer or who are there, who got the treatment and who did not get the treatment. You see, the process is very different. Previous cases, we are first doing the matching, then we are doing the testing for the balancing. Here, by inbuilt method, I'm going to think of covariate balance in the estimation by reweighting the data set. So I want to ensure that the pre-processing is nothing but a maximum entropy reweighting scheme that assigns weight to each unit such that the covariate distribution in the reweighted data set, because I am doing the reweighting, satisfy a set of moment condition. And the set of moment condition, you can do it based on the mean, you can do it mean variance, you can go up to mean variance skewness, whatever way you want to think about it. In general, people do mean, maximum people go about the both, which is the mean and the variance. Covariate balance, what is the advantage? Is directly built into the weight function, okay? And that's used to adjust for the control units. And we use exact balance on the first order moments in general, which is the mean of the covariate distribution in the treatment and the reweighted control group. So note, here if you think of it, I have people, I reweight them in such a way that the mean of the two, the control and the reweighted treated and the reweighted control is almost same. So by the process of entropy, I build my balancing already, right? Clear? That's more or less. Things to remember, what are the major points that we try to think about it? First, control unit could be replaced once it is matched with a treatment. Okay? Thus, a control unit could be selected more than once, right? So I can have more than one the same control unit because I am going to do something like replacement based one. Matching with replacement minimizes the propensity score distance between what? Between the matched unit, and because each matched unit or the treated unit is then again matched with their closest control, right? Because I am doing replacement of the controls, okay? Clear? Fine. Second, each treated unit could be matched to an arbitrary number of controls. I don't know how many of them, as you said, how many of them I am going to pick as my control. I have no idea. I can pick everybody, I can pick a selection, but that would be depend on the procedure that I am going to follow. Okay. Third, before performing the matching, a common support region can be defined. So what is a common support region, right? So common support region, think of it very carefully, excludes the treated units whose propensity score, so appearing, the probability of appearance is higher than the highest propensity score of the control units. So that's for the treated group. For the control group, I'm just going to reverse the mechanism. So for this group, it is higher. So for the control group, it must be the opposite of the higher, which is the lower, right? Whose propensity score are lower than the lowest propensity score of the treated unit. So you estimate the model, say a probit function, right? You get the predicted probability. You know the predicted probability of both guys in the sense the treated and the control. I now want to think of, I'm not going to take those people whose predicted probability is higher than the highest propensity score of the control unit. So I can calculate the max of the predicted probability of the control. I have also the predicted probability of the treated. I'm going to exclude the predicted probability of the treated if it is higher than the max of the predicted probability of the control. Clear? Yes.
Why is this necessary?
Because so this is your one distribution, this is your other distribution, right? You do not want to take them into account. You want to take the intersection of those. I mean, you want to take the, what should I say, non-intersection of those guys. Clear? Because these are something like, you can think of, these are the guys who lies in the tail of the distribution. These are the guys, and in this case, you think of it very carefully. So this is the line. For the first, I'm going to exclude this group. So the right hand side of the tail of the distribution, right? Highest. That is why right. For the left, lower. That's why the left. Clear? So I'm then going to think of, that I'm going to do the same process for the control, but exactly following the reverse way. It's very intuitive in some way. Why do I do this in a way? Right? Clear? Fine?
So can we skip out on the information about the treated units which have a higher propensity?
Of course. And
That's
then,
losing information.
yeah. But I think you should lose that information, because those are the weirds staying over there on the right hand side of the distribution. And then the other one are the weird which lies in the left hand side of the distribution.
Then when using the score of the control groups,
Yeah.
is it possible that some information has been missed out on a control?
No,
That is why there are certain.
I mean, one way to think about it, you impose common support, you don't impose common support, and see the results. But the tradition to do it is impose the common support, because you do not want to take these guys. Similarly, you do not want to take the other side of the guy.
Is there a range within which, let us say, if I'm looking at the score of the.
Because it is automatically gets calculated, right? Because I have p hat for the treated and max of the p hat of the control. I exclude those guys where the p hat I is greater than the max of the p hat control. I then exclude the p hat I of the control if it is lower than the mean of the p hat of the treated. That's a simple procedure. Clear? So I do it both for the right hand side as well as the left hand side of the distribution. Yes?
So in this entropy meter,
Yeah.
so basically what we are doing is, in the control group, suppose I have age of firm, and I have 10 firms. So now for each firm, I am just taking the average of every firm and then matching it with the treated group.
Yeah.
So
Or the variance.
in a way, now I'm removing the time dimension that would be different.
No, not time. It is a cross section data. There is nothing like time dimension. Okay. So balancing test should always be done in some way. Okay. This is your homework. Yes, please.
This common support region, the third point is on there.
Yeah.
Actually, there were two things. One is the you mentioned about the distance,
Yeah. Yeah.
distance
Yeah.
method for
Yeah.
selecting the
Yes.
control group.
Absolutely.
Matlab, using it as this method.
Yes.
So my query was about the is it based on the covariate itself?
Yeah. You can do it based on the covariate characteristics itself, or based on the probability that you are calculating in terms of participation or getting the treatment in terms of the covariate. So when I do it based on the covariate's characteristics by taking the deviation, and with my variance covariance matrix, I call it matching.
And the software itself
does it. Yeah. So this
suppose
is,
I do 100
let me finish. So that's my matching. Matching can have two parts. It could have like Moll-Lewis distance or nearest neighborhood. Remember, nearest neighborhood is nothing but a Moll-Lewis distance with stringent criteria. Then I come to prediction of the probability that you would participate or you got the program, right? There I call it propensity, because remember, the propensity, whenever I use the term, it's a probabilistic term. It's a probabilistic term. So that's why I'm calling it propensity, and hence I'm calling this as propensity score matching compared to the matching methods. So matching methods can be NN and MD, right? So matching can be covariate matching, propensity score matching. Under the covariate matching, it comes NN and MD. Under the propensity score, I can think of radius as well as the propensity score in kernel way, right? Then there would be another one which is completely different from all of these guys, which is my entropy balancing. So if I have a line, I have three parts. One is covariate matching, one is propensity score matching, one is entropy balancing. Entropy balancing is a game by itself. Now I have this covariate matching. Covariate matching has two parts, nearest neighborhood and then Moll-Lewis distance. Propensity score has two parts, radius or caliper and the kernel. Then I go to the entropy balancing. So overall, I am thinking of there are 5 different ways I can do the matching exercise. And sorry,
The common support region.
is mainly applicable when you are thinking of the propensity score matching, right? So for your second part, the radius as well as the kernel, you can think of the common support program. I mean, you can do a common support even in case of nearest neighborhood, but well, yes.
So we can do a PSM if there is a disproportionate sample between treatment group and control group.
Yeah, yeah. Ideally, people think that, it should be 30, 70, 40, 60, something like that, right? But if I forgot. So, so you see that this is what it is. This is your actually a tutorial. So the way I talk about it, it is covariate matching, which I am claiming as distance matrix, right? So distance matrix has two parts, nearest neighborhood and Moll-Lewis distance. You see that? Then I come to propensity score, which has also two parts, radius and the kernel. And then my last one is entropy balancing. Clear? Fine. So this is your covariate matching, distance matrix. It has two, nearest neighbor, Moll-Lewis distance kernel matching. Then I come to propensity score, has two parts, radius and the kernel. And then the last but not the least, which is a different form of a beast, is nothing but entropy. Okay? Clear? And this is what you have to do today. You have to replicate this table, if I recall correctly. Yes,
Sir, when you told us about
I didn't tell anything.
when you told us that the average treatment effect is average treated ATT plus ATC.
Yeah,
So we're just looking, many of our the impact evaluation studies we do.
yeah,
So we just found out that the net gains, like
yeah.
productivity in group A is higher by
Then,
this much.
yes,
Like we do it in this percentage or some productivity gain or something that.
yeah.
But here we are through this method we're trying to infer for the entire population that if this
No, entire population you can do, which is ATE,
it
but
is related to
yeah, but ATT is only for the group of people who got the treatment.
so our objective should be
Treated, average treatment effect on the treated. Clear? Fine. I'll take a break now.
क्या हुआ हाँ हाँ क्या बोला हाँ तो लग रहा है पूरा आईवी आज प्लानिंग की थी